till now we have studied that there can be more than one method for solving the numericals involving symmetrical fault in a power system. One can be the Thevenin method, and other can be either mesh analysis, node analysis, or any other method which involves network theory only. Now, in this lecture, what we will see how to utilize the bus impedance matrix in fault calculations. We will also realize that fault calculations, if the power system is very big, there are number of buses in the power system, then it is better to utilize the bus impedance matrix for finding various currents during a fault. So because of this, we will be able to know the importance of the bus impedance matrix. So the question arising in the minds of various students, that why do we need a bus impedance matrix for fault calculation and the admittance matrix for load flow studies, will be clear now when we will study the importance of bus impedance matrix during fault calculations. Now let us see how to find the utility of bus impedance matrix in solving any problem of faults. Here in the figure, I have shown a typical power system, very simple power system containing 4 buses and the reference bus. Now there are some assumptions which I have made. What are those assumptions? That is the pre-fault current, that is any current is equal to 0 before fault. What does it imply? It implies that there is no current in the system, then the voltage at bus 1 is equal to voltage at bus 4, bus 3 and bus 2. So it means that the voltage at various buses V1 is equal to V2 is equal to V3 is equal to V4 when there is no fault current, there is no current in the network. It can be clearly seen from Ohm's law also. Since there is no current, there will be no voltage drop in this given admittance. So the voltage at these 2 buses will be equal. Now what I am assuming now is that, let us say that the voltage at bus 4 is equal to V4 and I am writing it as Vf. Okay. So what I can do now, since there is no current flowing in the system and the voltage here is Vf, then even if I connect a voltage source like this, whose value is equal to Vf is equal to V4, then again there will be no current flowing into the bus. Why? Because already the voltage at bus 4 is V4. Then even if I connect a voltage source equal to V4, then there is no potential difference existing between the source and the bus. So again there will be no current flowing into the system even if I connect a voltage source here. Okay. Now what I will do, I will try to simulate a fault now. What I will do, I will try to simulate a fault on bus 4. So how can I simulate this fault? Let us say that there is a bolted symmetrical 3-phase fault. Bolted fault means that there is no fault impedance. Okay. So when there is a fault on this bus 4, then the voltage of this bus 4 will be equal to 0, because there is a bolted fault, then there is no impedance given in the fault, then no matter how much current flows, there is no voltage here, and this voltage will be equal to the reference bus since it is representing a fault like this. Okay, so the voltage of this bus will be equal to 0 Now, how can I simulate this? I can simulate it if I connect a voltage source here like this. Which is opposing this voltage source. This sign represents the AC and this sign represents the instant when the voltages are positive at various nodes. Okay. If this voltage source is having value equal to Vf equal to V4, then by KVL I can see that the voltage at bus 4 will be equal to 0. So it is like simulating a fault on bus 4. If I want to write it as minus Vf, then what I will do, I will change the sign and I will represent the source like this only. Okay. So as of now, I have tried to simulate the fault on bus number 4. Now, what we will do, we will try to find the voltage drop because of the source which we have connected to simulate the fault. Now, earlier there was no current in the system when this source was connected, but when this source is connected in the system, now what will happen? There will be some current going out from bus 4. It will be equal to minus of I4, because usually in the study of power system, we take the positive sign for the currents which are entering into the node. But during a fault, what will happen? The current will come out of the bus 4 and it will try to go to the reference bus. Okay, let us say this is current minus I4. So you see that this current will be only because of this voltage source which we have connected to the system to represent the short circuit or the fault. Okay, so what it is like we are trying to use the superposition theorem here. Since the network is linear, I can easily utilize the superposition theorem. Then in the initial case, there was no current in the system, and now what I am trying to do, I am deactivating all the voltage sources available in the system. Okay, now I have deactivated this source, I have deactivated these sources. Okay, only this source is now in the network. Then it shows that by superposition and from the reasoning which I have just given, that this source is responsible for the flow of this current, then I can see that in the system now the current flowing out of the bus 4 will be equal to the fault current. Okay, so I can see that during the fault, this current is equal to the fault current which is flowing out of the bus 4. Now what I will do, I will try to write first the Ybus of the system and I will try to write the equation of power system in the form I is equal to YV, where V is the bus voltage matrix, this is the current source matrix, and this is the bus admittance matrix. Okay, now I will write the bus admittance matrix for the system, which is very easy directly since all the admittances are given, and I will write this directly in the next slide. Now here I have written the bus admittance matrix directly. I have just shown this how to write the bus admittance matrix. It is just equal to the all the admittances connected to bus 1, 3.33, 4.0 and 5.0. Okay, I have taken J outside. Now this is the fault current which is if I am using the subtransient reactances and the voltage behind subtransient reactances, then this is the subtransient fault current. Now this IF double dash is equal to minus of I4. So when I will write the equation I is equal to YV, then I will write I4 minus of I4 if is equal to IF double dash, then I4 is equal to minus of IF double dash. Okay, so what I will do, I will write the equation using the fault current in terms of the fault current. Now we are just trying to find the effect of this source when all other are deactivated. Now you can see then there is no current source connected to either of the buses. So all other current sources are 0. So this is I1 is equal to 0. Similarly I2 is equal to 0. I3 is equal to 0. But I4 is equal to minus of IF double dash. And this is equal to the bus admittance matrix. J is common outside. Minus 12.33, 0, 4, 5, 0, minus 10.83, 2.5, 5, 4.0, 2.5, minus 17.83, 8, 5, 5, 8, minus 18.0. And in the voltage, bus voltage vector, what I will write, now what the voltages will represent, these will represent the change in the voltage of the various buses due to the current by this source only. Okay, that is, it is going to show the contribution of this voltage source to various bus voltages. So if I want to say, I will write that it is just like V1 delta, that is the change in voltage because of the current induced by this voltage source in the system. Okay, similarly V2 delta, V3 delta and V4 delta. Okay, so you can see from here that if I write it like this, if I take the multiply this everything by the inverse of y, that is, if I write y inverse I is equal to y inverse y into V, or if I write this is equal to I only, unit matrix only, so it will be the bus voltage matrix is equal to, and this Y inverse is nothing but the bus impedance matrix G into I. Okay, so you see I can find the voltages at various buses just due to this voltage source which is representing or simulating the fault on the system. Okay, so you see that instead of using the admittance matrix, if I use the equation in this form which utilizes the impedance matrix of the system, I can determine all the voltages at various buses or the change in voltages due to the fault, and because of this I can find the current in the system. Since I will know the value of voltage at each bus V1, V2, V3, V4, then just using by Ohm's law I will be able to find the current in every part of the network. So in this way we can see that during fault studies bus impedance matrix is much better or much easier to be utilized in the numerical problems. Okay, now what I will do, I will try to expand this equation further in the next slide to see the effect of this fault current on various buses more deeply. Now what I have done, I have expanded the bus impedance matrix in terms of Z11, Z12, Z13, Z14 like this for every node. Now you know that what we have done, we have deactivated all other voltage sources or current sources available in the network. That is, I have disconnected or made them equal to 0. This is 0, this is 0, this is also 0. So what will be the value of V4 delta? This is the reference bus and the voltage source connected is minus Vf or minus V4. So the value of the bus voltage at bus number 4 will be equal to the value of this voltage source. So V4 delta is nothing but minus of Vf. Okay, so I will write it here, minus of Vf, and all other are V1 delta, V2 delta, V3 delta. This delta, as I already told, represents the contribution to the various bus voltages by the current being flown into the network due to the connection of this voltage source, which represents kind of the fault on the system on the bus 4, is equal to Z11, Z12, Z13, Z14, Z21, Z22, Z23, Z24, Z31, Z32, Z33, Z34, Z41, Z42, Z43, Z44, and this is 0, 0, 0 minus IF double dash. Okay. Now from this row I can clearly see that minus Vf is equal to minus Z44 IF double dash, or the value of fault current is nothing but IF double dash is equal to Vf over Z44. Now this result is not very surprising. Why? Because this impedance represents the Thevenin equivalent impedance of the network seen from the bus 4. Okay, so we have seen in our previous lecture, if we solve the given network during the fault by Thevenin method, what we do? We take a voltage source Vf and the Thevenin equivalent of the system seen from the point of the fault. This represents the power system of the during the fault, and this is the switch representing the fault. Okay, so this Z Thevenin is nothing but Z44 here. So the fault current is just equal to Vf over Z Thevenin, and it is here now Vf over Z44. Okay, so if there is a fault on, let us say, bus N, then the fault current can just be simply written as the pre-fault voltage over the Thevenin impedance seen from that bus. Okay. Now the change in voltage, let us say I want to find the change in voltage due to this fault current at bus 1. So V1 delta is nothing but this multiplied by this is equal to 0, this is 0, this is 0, only equal to minus of Z14 IF double dash. Okay, or if I write the value of IF double dash from here, it is nothing but minus of Z14 into Vf over Z44, or V1 delta is nothing but Vf, minus sign is outside, Z14 over Z44. Now to generalize, if I say that the fault is at, let us say, bus N, then I will change 4 to N only. It is equal to minus of Vf Z1N over ZNN, where these represents the elements of the bus impedance matrix. Now, this is just the change. What will be the final value of the bus voltage? It will be nothing but the value of bus voltage when these all other voltage sources are activated in the system. What was that? It was nothing but just V1. So the final value of bus voltage, final, will be the voltage initially and the change in voltage due to the fault, which is nothing but this. So it comes out to be V1 minus Z1n over Znn over Vf. So in this way, I can find the voltages, final voltages at various buses after the fault. To generalize, I can write voltage at the kth bus is nothing but Vk initial minus Zkn over Znn into the fault voltage. Okay, the voltage existing in the system at the fault point before the fault happened or the fault occurred. This is the voltage Vf. Okay, so let us say this is equation number 1. Now this equation will be very useful in determining the kind of physical equivalent circuit in terms of various elements of the bus impedance matrix that we will see in the next slide. Now there is one more important point. I can further simplify this equation 1 like, as I already told in the beginning of this lecture, that I have assumed that there is no current before fault. So all the voltages V1 is equal to V2 is equal to V3 is equal to V4 is just equal to Vf. Okay, so instead of writing Vk, I can write Vf in equation number 1. So voltage at bus K after the fault is nothing but Vf minus Zkn over Znn into Vf, or it equals to Vf 1 minus Zkn over Znn. So in this way, this is the kind of final equation for a system when there is no current before the fault in the system. So using this equation, I can find the final values of bus voltages at various buses. Now, since I know all the bus voltages, let us say this is V1 final, this is V4 final, this is V2 final, and this is V3 final. Now, if I want to find this current, let us say this is current IA. What I will do, to find the current IA, I will write V1 final minus V4 final over, let us say this is equal to ZA. ZA is equal to nothing but 1 over minus J5, because this is in the admittance form. And to write Ohm's law, I will write in the impedance form. This is nothing but ZA. So in this way, I can find all the currents in the given power system once I know the bus voltages. Now you see that the bus voltages are easily found if I use the bus impedance form of the equations instead of using the bus admittance form of the equation. So in this way, we can clearly see the importance of the bus impedance matrix during fault calculations. Now in the next slide, I will try to make a very crude equivalent structure in terms of the various elements of the bus impedance matrix that we will see in the next slide. Now in this figure, I have drawn something called as a rake equivalent network of the power system. What I have done, I have tried to show all the buses, bus number 1, bus number 2, bus number 3 and bus number 4. Initially, when the switch is open, that is, there is no fault on the system, it is assumed that there is no current in the system. So what does it mean? It means that all the voltages, if this is the voltage Vf here, will be equal to Vf, Vf, Vf and Vf. That is, initially V1 is equal to V2 is equal to V3 is equal to V4 is equal to Vf. Okay. Now, these are the Thevenin equivalent impedances seen from various buses. Okay. These Z11, Z22, Z33 and Z44. Now, this switch S represents the simulation of fault on bus number 4. When this switch S is closed, it will simulate the fault and a current IF double prime will flow, which is equal to minus I4. That is, it is going away from the bus number 4, and then it will represent the faulted power system. Now what I have done here, I have tried to show the transfer impedances also by using these curly brackets. Like this first larger one curly bracket represents the transfer impedance between bus number 1 and bus number 4, represented by Z14. Similarly, this represents Z24 and this represents Z34. Okay, so from our previous slides, what we know that IF double prime is equal to minus I4 is nothing but Vf over Z44. Okay, and the change in voltages at various buses now can be kind of represented just by the multiplication of IF double dash into various transfer impedances. Like this represents impedance represents some kind of impedance connected between bus 1 and bus 4, which will be showing the change in voltage or the voltage drop at bus 1 due to the current IF double prime flowing from the bus 4. Okay, so V1 delta will be nothing but minus IF double dash into Z14. Similarly, V2 delta will be nothing but minus IF double dash into Z24. So this reg equivalent network is kind of physical representation of a network in terms of the elements of the bus impedance matrix. As I already told in one of the previous lectures that it is not possible to actually draw the physical equivalent network from the bus impedance matrix. This is the closest which we can get in terms of the transfer impedances. So this cannot be physically realized, but this kind of gives us a feeling how to understand the importance of the transfer impedances. Okay, so in this way the importance of bus impedance matrix can be understood just by seeing these transfer impedances and the Thevenin equivalent impedances seen from various buses. Now in the next slide, what I will do, I will try to introduce a very small but very important topic of short circuit MVA of a power system.